Hey everyone, I am Sarah Fahouri. I'm currently a doctoral candidate at Washington State University. My research is at the intersection of cognitive neuroscience and software engineering. And I'm super excited to be here today. And I'm going to talk a little bit about how software engineering researchers are using neural imaging to study the cognitive impact of code. And I have a few actionable tips to reduce the cognitive burden of the code that you write. So I think every developer can relate to at some point feeling incredibly frustrated reading someone else's code, right? It's kind of like weeding through a jungle. And once the jungle clears and you start to understand a little bit more, you start questioning decisions made by the original author. Like, why did they use this structure? And where does this bridge possibly lead? And then you see a sign that says, this is a bridge, and that's seemingly useless documentation. And trying to understand complex or inefficient code can be cognitively exhausting. So you end up wondering, like, what was my colleague thinking when they were writing this code? And even worse, it can be past you from like a week ago. This is your own code that you're reading and you have no clue what's going on. And, we're all trying to look for ways to grow as developers. So I think it's interesting to look into the question, how can we write code that's easier to understand? And the first place to start in order to answer that question and avoid, having this jungle of code for our future selves and our team members to look through, is to really have a fundamental understanding about what makes code difficult to comprehend in the first place. And there are some obvious things, right? The first thing that comes to my mind is, well, code that's not formatted well, that makes things hard to read. So these are two snippets. They're doing exactly the same thing. One just has really bad formatting. And so, of course, it's much harder to read. But does that mean that it's difficult to understand? And I don't think necessarily that it does, right? Once you are able to read the code, you realize that, okay, this snippet is pretty straightforward. I can reason about what it's trying to do fairly easily. So it's not difficult to understand. It just has poor readability. Then on the other hand, you have something with great readability, right? It's just one line of code. It's easy to get through, but this example is difficult to parse and understand because there are many different conditions to keep track of. They're nested, right? But shorter and more concise code doesn't always mean that it's easier to understand, right? So here are two snippets that are doing exactly the same thing again. But the one on the top doesn't have any informative variable names, and it's using magic numbers like 12.5 and 150. Whereas the version on the bottom defines what those magic numbers are, and it has really informative variable names. So when you're creating a mental model and executing this code mentally, instead of saying, okay, what is I, what was J again? What is temp value doing here? You can say like, okay, we're looping through all of the rows, all of the columns of this matrix, and then we're multiplying by the pixel normalization factor instead of just 12.5. So it definitely makes it easier to comprehend and understand what's going on, even though the snippet on the bottom is less concise and maybe a little bit longer. So how does our brain actually process code? What's going on in our brain when we're reading code? Well, we know that our brain is using multiple areas of the brain, right? It's not just one, but it's very heavy on working memory, right? We create these mental models of code using the syntax and the semantics, and then we mentally execute the code, and we store information like variable state, what loop we're on. We store all of that in our working memory. But when code becomes too complex and there's too much to hold in our working memory, the code becomes difficult to reason about and understand. There's only finite room in our working memory. It's not this infinite resource. So sometimes we have to go back and reread like, oh, what was I again, right? What was this variable state at this point in time? And this is defined as cognitive load, right? It's the total amount of mental effort being used in our working memory. And so when code becomes more difficult, we use more of our working memory and we increase our cognitive load. So if we want to write code that's easier to understand, it makes sense to study this from the perspective of cognitive load, right? And understanding when is code causing high cognitive load, and can we write code that is less cognitively taxing? And, we have styled guides that are designed specifically for this purpose to make code easier to understand, right? And style guides are pretty binary. They'll say things like, do this and don't do this, right? Like, use camel casing, don't use global variables. And, there's pages and pages of recommendations, but which are the most important practices? And what's the cognitive cost of each of those practices? What's the cognitive cost of using well-structured code, well-formatted code versus not? And researchers conduct experiments to get empirical evidence about the best ways to write code that's easy to understand, and that's how these practices come out. But we don't have any empirical evidence about how these practices affect cognitive load, right? And how could we do this? How can we start to identify the cognitive cost of different practices? And I think the most common way, and the way that researchers use right now, is to just ask developers, right? You conduct a controlled experiment, isolate a feature that you want to study, and then you just ask, was this code snippet difficult to understand? And so we call these self-reported measures, right? Where the developers are telling us how difficult something is, or we're inferring it from a comprehension summary, right? But there are some issues with the accuracy and authenticity of self-reported verification from surveys and think aloud protocols, right? For example, participants in a study might have personal biases that cause them to underestimate their ability, so they might inaccurately rate task difficulty. And here's an example. I'm a researcher and I want to compare how difficult a task is across all of my participants. So I'll use something like a Likert scale. On a scale of 1 to 5, where 1 is super easy, 5 is very difficult, and it's a standardized scale and it allows me to compare across participants. So in theory, it sounds great, but this might be one of the thought processes of a participant that causes them to incorrectly rate task difficulty. So they might think that, at first this task was super hard, but then I realized that that's my fault. I completely misunderstood what was going on and I made a mistake. So I won't factor that into my rating scale, and I'll rate it as a 1 out of 5. It's super easy because that's on me. That's not the objective rating of the snippet. And so you can see how that's very terrible for researchers, right? As a researcher, I want to know if you made a mistake while trying to understand something, because chances are many other people will as well. And that's a huge factor in probably the aspect that I'm studying, but how to increase comprehension of a piece of code. How can we avoid those mistakes, right? So self-reported measures are, prone to biases. They can be misleading, and they're not perfect. So are there more objective measures out there? How can we measure the cognitive load caused by code in another way? So we can learn a lot from other researchers who are studying working memory in different domains, like in cognitive neuroscience, right? And they're using neural imaging to quantify cognitive load for different tasks. And it all boils down to this concept that different areas of the brain that are active have higher demands for oxygenated blood. So the harder a certain area of your brain is working, the more oxygenated blood rushes to that area. So if we can measure the amount of oxygenated blood in the areas of the brain associated with working memory, then we can quantify cognitive load, right? And if we can measure cognitive load on developers that are reading code, then we can quantify the effect of that code on the working memory areas of the brain. And this is exactly what we do in our research. We use a brain imaging technique called functional near-infrared spectroscopy, or FNIR for short. And This is exactly what it does. It measures the amount of oxygenated and deoxygenated hemoglobin, or blood, using near-infrared light. And we measure it over the prefrontal cortex. And that includes an area of the brain that is associated with problem solving and working memory. And the great thing about FNIR is that it's used in a wide variety of working memory research. And it allows replication of real working environments. So look at that picture. It's basically just a headband. And it's not too uncomfortable compared to other brain imaging techniques like MRI, for example. And it allows us to put this brain imaging technique on developers while they're at their own desks using their own computers, programming in an IDE. And the best part is that it can be paired with eye tracking. And so if we can combine information about the cognitive load that a developer is experiencing at any given moment in time and map that to specific identifiers in the source code using an eye tracker, for example, then we can obtain this super interesting information about specific identifiers in the source code and how hard someone's brain is working, right? And how much cognitive load they're experiencing while they're reading that area of the code. And so this is what eye tracking data would look like, right? We're just tracking where a participant is looking in the source code. And in this example, they're typing a line of code, and we can see that they're looking where they're typing, and they're looking a little bit at their surrounding code as well. And then we can pair that with cognitive load data. So you can see at the top, we have a graph showing the amount of oxygenated and deoxygenated hemoglobin in the brain. And we're able to map that cognitive load data to specific areas in the code using the eye tracking data. And then the colors of this heat map that you're seeing are corresponding to the amount of cognitive load. So dark red means high cognitive load, and blue means light. And so now we can create these more objective models of cognitive processes and understand how different constructs are affecting cognitive load. So we have this really great framework. There's this really famous quote by Phil Carlton. There are only two hard things in computer science: cache invalidation and naming things. And I love this quote so much for many reasons. But now that we have a more objective framework to model cognitive processes and cognitive load, the first thing we wanted to study is how important is good quality documentation, picking the right variable names? And what's the cognitive cost of not doing that? And the literature tells us that source code lexicon is incredibly important to program comprehension, right? It's not even debated. So can we see the impact of source code lexicon on cognitive load and developers' productivity? So we ran an experiment with 25 developers. We set up the FNIR and the eye tracker. We hooked everyone up, and we asked them to find a bug in a source code snippet. And we designed the task where there's two snippets, they're exactly identical, they have the same code, the same bug. The only difference between the two snippets is that one had poor quality lexicon. So the code had poorly named identifiers, outdated comments, incorrect comments, and the poor quality lexicon, the issues that we injected into those snippets were not out of the normal. They were snippets and issues that are widely found in our code bases. And they're actually called linguistic antipatterns. And they're defined in the literature as poor practices that cause inconsistencies between naming, documentation, and then the actual implementation of the software. And so essentially what linguistic antipatterns do is they cause inconsistencies in the mental models that we build when trying to understand a piece of code. They're misleading and they're confusing. One example is this set method that's returning something. So if you were to see the API call just set breadth without seeing the method definition, you would think that it's just setting the breadth, right? You wouldn't necessarily expect it to return anything because that's the convention. Set methods should not be returning anything. But in the implementation, it's creating a new object and returning it. So there's this inconsistency between what you're expecting the method to do and what it's actually doing. Another example is this get method. This get method is great. It's doing what it's supposed to do, right? It's just returning a value. But from the method name, again, you're expecting get expansion. So you're expecting to return an object called expansion, and that's a singular object. But instead, the return type is a list. So you're getting a collection of objects. So again, there's this inconsistency between what you think will be returned and what is actually being returned. Inconsistencies and linguistic antipatterns can also exist in the documentation. So if you read this summary comment, it's describing what the method is doing, and it's saying that it's trying to determine if the back button is enabled. But then if you read through the code, you realize they're using is forward enabled, navigate forward, right? Is navigate forward enabled? And so there's this discrepancy. Are we talking about the forward button or the back button? I don't know. And should I trust the comment or should I trust the implementation of the code? So there's this bug in my mental model now. And linguistic antipatterns can also affect variables. So is reached. If you see that variable being used, it's asking a question. The response should be yes or no, maybe a Boolean, right? But instead, it's an integer array. So what is this variable holding? I have no clue. And the same goes for stats. Okay, I'm expecting a collection of stats, maybe statistics, but the type is Boolean and it's set to true. So stats are true. It's a little bit confusing, right? So we wanted to study what happens if these very common code smells are inside of a bug localization task, and how do these affect the cognitive load of developers compared to the control snippet? So we compared our control group to the group that had the poor lexicon, and it turns out that linguistic antipatterns are misleading participants, and they're hurting productivity in very concrete ways. So the first is correctness. 65% of the participants could find the bug, but that's much lower compared to the 77% of the participants in the control task. And keep in mind, that's the same exact snippet, the same exact bug. The only difference is the variable names changed and the comments changed. And it took them almost twice as long to find the same bug. So almost 6 minutes versus 3 minutes for our control group. So that's a huge impact on efficiency and productivity. And most importantly, there was very obvious and significant increased cognitive load in our group that saw the poor lexicon. They had much more confusion to work through because of the linguistic antipattern, and their working memory was much more taxed than the people in the control group. And so these are no longer opinions or anecdotal advice in style guides, right? We have empirical evidence that our source code, comments, variable names, our documentation need to be kept up to date, and they need to be consistent. And I only went over a few examples of linguistic antipatterns, but there's a whole catalog, and I encourage anyone who is interested to go take a look at these. So if you remember our first example that we looked at the beginning of the talk, we had some obvious examples about what makes code hard to read and hard to understand. But we really wanted to use our neural imaging framework to see if we have empirical evidence that something like code structure actually impacts cognitive load. And so that's the next thing that we studied. And we set up the task exactly the same. So we have two identical pieces of code. They're doing the same exact thing, right? They have the same exact bug. The only difference is that one now has poor structure. And for the purposes of our experiment, poor structure meant that we changed the formatting, we changed the depth of nesting, we added some variables, all while keeping the same task and bug as the control snippet. And what we found that now even less people could find the bug compared to the control group, right? 55% compared to 77%. So structure really impacted their ability to correctly find a bug. And it also slowed them down. It took on average 4 minutes versus 3 minutes for the control. But what's interesting is that they were faster than the group who had poor lexicon. And participants were very frustrated when reading poorly formatted code with poor structure, and they were talking about it a lot too, right? They were like, oh, this code is terrible, I don't even want to read it, right? But what's interesting is that even though it was frustrated, it wasn't taxing on their working memory from what we measured, right? It didn't have a significant impact on their cognitive load. So they were difficult in a different way, right? And there's different aspects of what makes code complex. And poor lexicon created inconsistencies in the mental model, but poor structure just made the code hard to read and wasn't necessarily taxing on working memory. So one of the biggest keys to becoming a more productive developer is writing code that's easier for you and your peers to navigate. And we saw that there's several different factors that make code difficult to understand and difficult to navigate. So code might be easy to read, but hard to understand, or hard to read and easy to understand. And poor practices have different costs, right? We saw that some are more taxing on working memory resources, like linguistic antipatterns, whereas some greatly impact readability, but don't necessarily tax cognitive load. And what's nice about neural imaging is that now we can start getting a deeper understanding of the different types of complexity that can arise in code. And we can become better programmers with this information. And one actionable tip that we saw today was to make sure that our comments and variable names are semantically consistent with their usage by avoiding linguistic antipatterns. And we saw that code that has high cognitive load can slow you down and have cascading effects on productivity for future you and your team, right? Our naming and documentation choices now have tangible impact on our readers' brains, and we have empirical evidence for this. As researchers, we really strive to produce research that's applicable to developers' daily work and improves your workflow. And so I'm really interested to know what you guys want to see studied next. How can we apply this framework? What features should we study? For example, some people are deeply invested and highly passionate about static versus dynamic typing. Another question I have is, what do future style guides look like? Are we going to have cognitive price tags next to each coding practice? And what does a programming language designed using neural imaging look like? Reach out to me on Discord or Twitter anytime, and I'm happy to discuss with you all.